Okay, we continue our series of videos on inverse trigonometric functions, and we're going to define the arccosecant or inverse cosecant function. So, as usual, we start by looking at the y equals cosecant of x, and then if we switch x and y, x equals cosecant of y, that's a reflection over the line y equals x, but that is clearly not a function. So what we want to do is to restrict our cosecant down to where we get a one-to-one function but still keep all the y's. And this will boil down to basically half of a period here. So we're going to include between 0 and pi over 2. So we're going to definitely include this part. We can't include that because that doubles up y's. We could include over here, but that's kind of a skip. Be better to do this piece over here because it's a little closer. And so we'll end up with this part here, which is for x's between negative pi over 2 and pi over 2. Notice how that's part of y equals cosecant. So if we take that and reflect it over the line y equals x, that will give us our arccosecant. Notice that graph is part of the graph of x equals cosecant of y, but it's not the only values where x equals cosecant of y. There are infinitely many places here, but if we do this, this will be a function, in fact it'll be a one-to-one function, so that it is, if we put in an x value, that will give us a specific value, y, so that the cosecant of y is x, but it'll be a specific one where the y is between, well, let's look, between negative pi over 2 and pi over 2. Let's hide this one. You can see those are mirror images, right? Okay. And so this one has, for example, the point pi over 2, 1. So this one right here is the point 1 pi over 2. The cosecant has a point negative pi over 2, negative 1. So the inverse cosecant has a point at negative 1, negative pi over 2. So let's hide that one and just look at the arccosecant function, and we can see the graph there. Again, different notations like we had before. ARC, CSC, arccosecant, or inverse cosecant, sometimes written as CSC superscript negative 1. Not an exponent, but a superscript. And let's hide that definition, and let's look at some of the properties that it has. So, if you're finding the arccosecant of a particular x value, it's going to give you an output which is a y value over here. But we can think of that as an angle over here, which is the way we probably want to think of this. And so the output is an angle, we're thinking over here in the unit circle picture, and it's an angle between minus pi over 2 and pi over 2. Of course, notice that 0 is not one of those possibilities, so I've got that one kind of whited out there. What is the domain? Well, the domain is from negative infinity up to negative 1, including negative 1. Then we skip over and union that with 1 to infinity, including the 1. What's the range? Well, basically from negative pi over 2 to pi over 2 is the range, including those values, but it does skip over y equals 0, so it's negative pi, close bracket, negative pi over 2 to 0, open bracket, union, open bracket, 0, comma, pi over 2, close bracket. Right here you can see that. And notice that it doesn't have an x or a y intercept. It does have some endpoints. This one here in the third quadrant is negative 1, comma, negative pi over 2. And this one here in the first quadrant is 1, comma, pi over 2. Notice it is a one-to-one function. It's not continuous, though. It's discontinuous. It's broken into two parts. So we have two pieces. They're connected within them, the two pieces, but not between the two pieces. Within each piece it's connected, but the two pieces are not connected. So it's not a continuous. If you stay within one part, it's decreasing. So if you stay within this part, as you go left to right, it goes down. Same way here. Of course, if you switch from the left part to the right part, then it's going up. But it is a one-to-one function. Notice it's concave down here when x is less than -1 in the third quadrant. And it's concave up, decreasing for x in the first quadrant from 1 to infinity. So we can think of it between an angle between -pi/2 and pi/2, whose cosecant is a given angle. In a similar manner to what we did before, if we want to put this in on our graphing calculator, you can just put it in straight like it is, inverse cosecant on a Inspire. But if we want to graph y equals inverse cosecant of x on the computer, on the say a TI-84 like this, we want to be able to put it in here. Look at how we did that one that I have graphed there is inverse secant. Okay, we're going to very similarly do this. So this means that the cosecant of y is x, but not just anything. What is allowable for x and y here? Well, x's are -infinity to -1, union 1 to infinity, which is the y's on the, that's the output of the cosecant. But the y's, there's lots of different y's that we could have chosen, but we have chosen the y's from, back of the picture, from -pi/2 to pi/2, of course not 0. So -pi/2 to 0 union 0 to pi/2. Or basically we could just say from -pi/2 to pi/2, it's undefined at 0 there in the middle. But y's are definitely in there, but not 0. Could write it that way too. Okay. Now, cosecant of y is 1 over sine of y, and so that means sine of y is 1 over x, and y is the inverse sine of 1 over x. Now I have to be a little bit careful. What's the inverse sine of 1 over x? What can we take? What's the output? Well, it's between -pi/2 and pi/2, so everything's okay. These match up, and we're good to go. So if I put this in on my calculator like this and graph it, and I need a so it looks something like that, and that's basically what it's supposed to look like. So there is the Arccosecant function.